Good afternoon, everybody. I see a great number of people on the webinar, and we're very happy that you're joining us this afternoon. So thank you to everyone for joining us for today's webinar. It's Understanding Climate Impacts, Using Tools and Resources to Prepare Your Campus for a Changing Climate. My name is Anne Wapel, and I'm the Director of Communications and Science at Second Nature, and I'll be moderating today's panel. So just a few words, first of all, about who Second Nature is and why we're leading this webinar. If you're not familiar with us, we're the lead supporting organization of the American College and University President's Climate Commitment. And that's a network of about 680 campuses who have committed to carbon neutrality and to provide education for sustainability for all students. And that's what we're probably best known for, Second Nature. But in addition to this initiative, we have several programs that transform higher education in order to provide a sustainable society. And these programs are in about 3 other areas. Firstly, financing and policy. We're helping campuses to figure out appropriate mechanisms for financing sustainable practices in building and energy and other changes, and the policies to support meaningful change across higher education. So it's one area of programmatic activity at Second Nature. Another area that we spend a lot of time and energy in is in capacity building, particularly for under-resourced and minority-serving institutions. And Second Nature has a long history of being able to accomplish that across higher education. And finally, and where this webinar sits in our educational series, is in a resilience program. And we're initiating a new program to support campuses in identifying risks and opportunities related to climate and how to plan for resilient and adaptive campuses in coordination with local communities, which we feel is very important. So we're excited to be starting this new program as well as this webinar series, and there'll be lots of opportunity to engage with us both within this webinar and in the future. So a couple of quick logistics before we get started. We'll have a Q&A period after the 3 panelists have spoken, but feel free to submit your questions throughout the presentation on the GoToWebinar panel at the side of your screen. There should be a little area with a little bar that says questions, and if you just click on that, you can type your question in the panel right there. If it's a question for a specific presenter, please make sure to include their name when you submit the question, otherwise I'll have to make that decision for you. And at the same time, we'll be asking you some questions throughout the webinar. There'll be little polls that pop up a few times, and we'd love you to answer those so that we get a sense of what needs you have in terms of information and what you're doing where this webinar is of interest to you. So we're looking for information from you as well. And finally, to note, both the PowerPoint presentation and the recording of today's webinar will be available to you after the event, and we'll email that link to all participants after the webinar. And of course, we encourage you to go back and view that anytime, and of course, feel free to share. So hopefully that'll be useful. Okay, so let's get started with the webinar and introduce our panelists. So first of all, as I mentioned, this is part of a webinar series. A climate resilience focus for this series, and we're trying to help colleges and universities use some of the latest climate information to start to understand and assess the impacts of climate change both on the campus and in the surrounding communities. A lot of the information that we're going to be talking about comes from the National Climate Assessment, and we have several people in Second Nature who are really engaged in the National Climate Assessment, and we're very focused on helping to provide outreach and information to a broad array of people. So there's also going to be, other than this webinar that we're on right now, we're hoping to include some regional focused webinars, and we'd love to hear from you. Feel free to put this in the questions or in answer to a poll later on, how you would like to receive information about regional climate and what would be useful to you. We'd like to target webinars so that they're really valuable to you in your decision processes. Okay, so who do we have on the webinar today? Well, as I mentioned, I'm Anne Wapel. I'm the relatively new Director of Communications and Science at Second Nature. Up until recently, I was the chair of the National Climate Assessment Technical Support Unit at NOAA, and I ran NOAA's assessment program. And also on the call, who will be doing all the substantive talking today, we have Adam Paris, who's the program director of NOAA's Regional Integrated Science and Assessment program. We call it the RISA program. And he led the whole development of the Global Sea Level Rise Scenarios report, which was produced in support of the National Climate Assessment and involved what seemed like, I know, hundreds of people. For Adam, it was a really diverse effort, and he'll tell you more about that. And then we have Dr. Ken Kunkel from NOAA's Cooperative Institute for Climate and Satellites, and he's the scientist at large for the National Climate Assessment, which is an enormous job. And the climate scenarios that he'll be talking about today have been used directly in the National Climate Assessment to provide a lot of the underpinning climate science in that assessment, and is a reflection of the latest information that we know about national and regional climate and their impacts. So we have the best of the best on this webinar today, and I know that they have great presentations coming up. So just a few words of introduction about what we'll cover today. What we're focusing on today is the use of scenarios in particular. This is climate and sea level rise scenarios, how they were produced as part of the National Climate Assessment, where you can find them, and then we'll also highlight the potential climate changes at the national scale and in the regional scales. So we're looking at current impacts for the next few decades to the next century. I'll say a few words about the National Climate Assessment and how we came to produce these scenarios. And then we'll also try to relate what we're saying today to how you can use them. And we're certainly looking for more feedback on that as we go through this. This is the first in the series, and we hope to get more and more information to you at the scale that you really need that information. So please let us know how you're receiving this. Next slide, please. So just a couple of words about the National Climate Assessment, since it really is the sort of the connection point of what we're sharing today. In 1990, the Global Change Research Act was signed, and as part of that, there is a mandate to produce a national climate assessment. Approximately every 4 years, this National Climate Assessment should integrate, evaluate, and interpret the findings of the U.S. Global Change Research Program. This is a program of 13 different agencies across the government that integrates climate science and global change science across all of those agencies. It reflects about a $2 billion investment in climate and global change science across those agencies. So the national assessment was to pull all of that together to discuss the scientific uncertainties associated with the findings across the program, and then to analyze the effect of global change on a whole series of sectors that were believed to be important for the national economy and our national practices. These are very much, this was a very forward-looking legislation when it was written in 1990, and many of these sectors are still exactly what we would want to focus on today. This National Climate Assessment is actually going to augment those sectors as well, and right from the beginning we felt that regions were an important way of breaking down climate so that it's useful for decision makers. And so this National Climate Assessment has 9 regions as well, or 8 regions plus the nation, as well as these sectors. And finally, the legal requirement is that we analyze the current trends in global change, both human-induced and natural, and project what's likely to happen in the next 25 to 100 years. So a few things on the next slide that's also different about this National Climate Assessment. We've had 2 before, by the way. We've had one in around 2000, and we had another one in 2009. You'll notice that that's not every 4 years. What we're trying to do with what we have been trying to do with this National Climate Assessment is to create the capacity to conduct and use assessments on an ongoing basis. So it should be much easier to produce them frequently. But at the same time, we're trying to design it in such a way as we can have updates on various aspects of the climate when they're needed, not just every 4 years or even every 10 years as it has been done. So it's both providing this synthesis report-based assessment, and it's providing a sustained process, the output of which are things such as indicators of change and impact and success in terms of adaptation and mitigation, it's also providing things like scenarios. And this is an important outcome of this new National Climate Assessment process. So this is really allowing us over the last year or so to talk about these scenarios. And we hope with a sustained NCA, National Climate Assessment, we will get lots of feedback and over time improve even more these scenarios for decision processes. So hopefully that's a little bit of a background on the NCA. I would encourage you that if you have questions about how to engage with the National Climate Assessment, please let us know. There are lots of ways that you can contribute to and use the National Climate Assessment as well. The final report from the NCA will be out in the spring of next year. It's just about to go into a government review process. So it should be available publicly next spring, and we're looking forward to that. But the scenarios that we've developed as part of this ongoing process are available now. So what are we talking about with scenarios? Why are we talking about them? Why might they be useful? On the next slide, there I start to lay out a little bit about why scenarios might be useful. So in the way in which we might incorporate climate into decision processes, there are a variety of ways we can do this, but at some level, we generally will want to consider 5 different steps. You want to understand what's happening with the climate, and you want to understand your own system and its vulnerabilities. So that's the very first step, is where are we, what's happening, and what's likely to happen. An assessment then of where the vulnerabilities are, how those are changing is important. And then, of course, planning for what you would want to do about that, implementing the plans, and an important step, which is sometimes left out of these things, is evaluating success. And that's a real challenge right now in adaptation and adaptation and resilience. It's a very difficult set of metrics or indicators to develop to know really how well we're doing. But that's important because it helps us make good decisions about the cost effectiveness and value of making these decisions. And we're going to talk a little bit about what second nature might do there. So scenarios, which we're going to explain a little bit more about what they are, can either be considered an input to a decision process, and that's mostly what we're talking about today, is we're looking at sea level rise and climate scenarios as an input to decision processes. But scenarios can also be used as decision analysis tools throughout all of this process. You can use what's called participatory scenario planning as a way in which to incorporate information, do the assessment and the planning process as well. So, and of course, you can look at the implementation implications from this scenario process. What they are, though, really is a range of plausible futures. They are really sort of what-if scenarios, but with some more definition about what those future circumstances are. So we're not just guessing; they're plausible, but typically they're not projections or forecasts. Some scenarios will include more information about what's more likely or less likely, and so you can say, we're giving you a range, but we think the middle of this range is more likely, sort of like a hurricane forecast. If you look at, you have a cone of uncertainty about where it might make landfall, there's a center part of that which looks more likely, but the full range of risk is shown to you in a hurricane forecast. Scenarios are sort of similar to that, in that they look at a range of risk and sometimes include probabilistic information. So there are lots of challenges when we're trying to make decisions, almost in any circumstance, but particularly with climate change and things that are highly uncertain. The uncertainty itself is one of the main challenges. But also, we've got already underlying vulnerabilities that we have to assess in order to figure out how climate is actually going to change those vulnerabilities. To some level, there are acceptable vulnerabilities, risks we're willing to take, both not right now and in the future. But those are changing, and so how do they change? And of course, with all of our environmental decision making, it's not just one factor, but multiple factors. And so it's not just that when we have a heat wave, for example, it's not just the heat, it's also often drought, and it's often poor air quality as well. And so there's multiple factors that impinge on the system. And as you make decisions to moderate those influences, a lot of times the consequences of your decisions and the consequences of the climate change itself have multiple competing consequences. And so it's very challenging to figure out what we're seeing in the future and what we do about that, how that will improve our outcomes as an organization or a system. Scenarios are a very good tool for examining and exploring what those outcomes might be. The challenge for the climate experts in all of this is that we tend to, in my background is science as well, but when we tend to approach this as if you have all of the knowledge, then you should be able to make a good decision. And of course, that's not true at all. And science, the actual climate science knowledge, is one part of the first part of the decision-making process of understanding the risks and impacts. And so we really have to up our game, quite frankly, in terms of how we provide information to people that can be used. And scenarios is one of these areas that we're exploring to see if that's useful. We know people use it in decision processes. And so the National Climate Assessment is spending a lot of time and effort to try to improve our scenario information, scenario-based information. On the next slide, just a few more points about how this relates to decision making. Everybody at every institution, at every level, we have different operational requirements in our institutions or in our cities or campuses. And we have different levels of risk tolerance. What might be perfectly acceptable for one person or one institution to tolerate is catastrophic to another. And so there are different priorities in terms of what we're really adapting to in the future. We might decide that a good decision is just to prepare for a specific likely future. If we were to say we can tolerate everything up to a 2-degree temperature increase, then we're just going to make our processes and systems resilient to that level. And so we prepare for a specific future. We might decide that we're relatively not vulnerable at the present, and we think that we can make changes incrementally. And so it might be a step-by-step decision process where we adapt to what's coming up in the next 10 or 20 years, and then we'll see for a while, and then maybe the next 10 or 20 years after that. Some changes will lend themselves to that kind of decision process. Other changes cross thresholds that we actually have to adapt to right away and not use this step-by-step approach. There might be a specific adjustment or sort of a built-in point in your future processes where you think that that would be an appropriate time to reevaluate the system, and you think that that would be possible. Or you might make decisions that would be resilient to a range of futures, if that could be feasible. None of these are sort of hard and fast rules, and every situation will be different. And so it's useful to bear in mind the kind of decision processes you've typically taken before in order to think about how this scenario process would fit into that. In the next slide. So one thing, as we're talking about adaptation and resilience and preparedness, to note is that while we tend to think about adapting to a future climate, the reality is that the climate is constantly changing. Even if we were to reduce our emissions to the point that we are no longer changing the climate significantly, and frankly that won't be for many decades at this point, the climate is still changing. So there is not one future static goal and then we can say we're done, we're adapted, we have nothing else to do. We're going to constantly have to be adaptive to the future. And so in our decision processes and in our scenario planning, thinking about the flexibility of the system is as important as whether it is resilient to a specific change. And I'll notice while we're using adaptation and resilience and preparedness relatively interchangeably throughout this conversation, but what we're really talking about is anticipating future changes, understanding how we're vulnerable to them, and moderating that vulnerability in some way. And that's really what we're talking about as a whole set of principles. Okay, next slide. So how do you incorporate scenarios and decide which model is useful? Well, there are a variety of ways, and what we'd definitely like to hear from you throughout this presentation, what you find useful. One of the ways in which to approach this, instead of looking first at what is changing in the climate system, is to look at what's important to you in your decision process or in your institution or your system. It's a very much a value-driven approach. Part of that is about what your mission and objectives are as a business or a campus. Some of it is about what are your critical business processes. In other words, what must function in order for you to do your daily business. And sometimes that's more useful to think about than starting with the climate changes. This leads you then to think about, well, in those critical systems, what are the existing vulnerabilities? How are we impacted right now? But particularly how that will change. And a couple of things to bear in mind is in every system there are what you could call pinch points, or sort of narrowing in the systems where you don't have a lot of redundancy, you don't have a lot of alternatives. Where, for example, I live in Western North Carolina in the mountains, and we have 2 major roads in and out of the region. We have in the last decade seen several landslides on I-40, and so there's only one alternative major route for goods and services reaching the area. That costs the region hundreds of millions of dollars every time that happens. So transportation in and out of the mountains in that case is a pinch point. There aren't many alternatives. And so thinking about that in your system, where is the flexibility? And of course things like natural resources, how will you provide water, or how does the region grow crops, or all kinds of natural resources that you would need to think of. So there's an enormous list, and what we're trying to do in Second Nature on the next slide is to think about ways in which we might help campuses in particular, but in conjunction with their communities, really decide how to incorporate climate and what's a good decision process for you. So there's a lot of information out there. What we're trying to do is to build on that, synthesize it, and come up with a set of guidance for how to incorporate climate scenarios or other kinds of climate information into your decision processes. And we'd love to hear back from you on what a kind of form that guidance can take. What we're doing is establishing an expert panel in the next few weeks where they are the leading experts in the field, and they will begin to set down guidance about how to do vulnerability assessment, how to incorporate that into planning and implementation, and what it really means to be climate adaptive or adapted. And so we're looking forward to getting that established. And certainly, please let us know what you think about that plan and how we can be of most value to everybody. So I think that was all I was planning to say, and I think we can move on to Adam Paris, who I've known for several years now, and we always had a good time even while we were working very hard on some of this work for the National Climate Assessment. Adam is one of the best people I know in terms of synthesizing information that can be used in decision making. And we're lucky to have him on the webinar. So thanks, Adam. Looking forward to hearing your slides.
Great, thanks, Anne. Thanks for having me today. I'm going to talk about, that was a really great introduction, and I'm going to talk about using scenarios of sea level rise for coastal adaptation. Next slide. So why develop sea level rise scenarios? Anne addressed this somewhat, but I just want to provide some tangible evidence. So we have, obviously, one reason is we know that any amount of sea level rise in the future will increase the frequency and duration and magnitude of coastal flooding. In other words, any amount of sea level rise, and we've been experiencing sea level rise for about 100 years now, well, actually a couple thousand years, but we've been recording it on the U.S. coastline and coastlines across the world for about 100 years. And any amount of sea level rise would increase the number of and magnitude of floods. So most recently, an example would be what we saw in the New York and New Jersey during Hurricane Sandy. And just to sort of tie this back to the history of the National Climate Assessment, what you see there in the green document, Climate Change in a Global City 2001, was a report produced in association with the first National Climate Assessment. And in that document, many of the impacts of Sandy were actually forecasted. In other words, we knew at that time what some of the impacts of events like Sandy would be, and we knew that they could potentially increase in magnitude with things like sea level rise over time. And you can see that based on what we saw during the storm, we still have a long ways to go to get people to sort of make them more resilient, safeguard them from those kinds of events. Next slide. So with that in mind, and with, next slide, please. With that in mind, based on the desire to have scenarios for the development of the National Climate Assessment, as Ann talked about, we pulled together an expert team to begin to try to synthesize the literature on sea level rise. I'm not going to read all the names here, but the important thing that I want to emphasize is that the information that you're going to see in the presentation the different sorry, just having some technical difficulties. The information you're going to see in the presentation and the information in the document that we're referencing, Global Sea Level Rise Scenarios for the U.S. National Climate Assessment, was compiled by multiple federal agencies and multiple universities across the U.S. And so this is really an interagency perspective on the state of knowledge on sea level rise from the federal government, but also from our friends in the academy. Next slide. So this is just kind of reiterating some of the points that Ann made, but particularly in the context of these sea level rise scenarios, what we're talking about are trajectories of environmental change, and primarily for the purpose of risk and vulnerability assessment, but also for planning and decision processes. They're not, as we're defining them, predictions or projections of what will happen specifically, and they're not formed under the assumption of reducing uncertainty. In other words, we know that we're still learning about the physical processes in the Earth system, as well as the biological and ecological processes. And as we learn more about sea level rise, we start to realize that there are different aspects of the Earth system that we maybe didn't know about as much. And so, we're still learning how to think about sea level rise in the future, and some of these processes are still unfolding. Next slide, please. So, again, just reinforcing some of the things that Ann was talking about, why use multiple scenarios? So scenario planning and scenarios it was actually a decision process and a tool that was developed after after World War II, I believe. But anyway, it was primarily used by the military at first and has been adopted in other countries and by the business community. But this is a nice illustration that just sort of shows the difference between a decision process that's based on scenarios and a decision process that's based on, say, forecasts. So if you have some probabilistic or definitive view of what the future is going to look like, perhaps it's in the near term, and perhaps you have a relatively constrained set of conditions that you're managing, and you have a more quantitative depiction of the future, then you might do something like forecast planning. But if the future is relatively uncertain and you have a lot of different factors or conditions that you're managing, it could be sunny, it could be rainy, it could be thunderstorms and lightning, then you might actually consider planning what you would do in any one of those cases. And the fact that you consider your decision and your decision pathway and how you might manage your resources in any of those futures then makes you more resilient to change because you're actually better prepared. Next slide. So, in the context of coastal management, coastal managers and local city and state governments across the U.S. that are located on the coast are really concerned about sea level rise over the long term and over the short term, but they're really trying to figure out what is their coastal community going to look like. And when they turn to the scientific literature, this is, a snapshot or a summary of what they might see. So these are a number of different studies in the literature on what future sea level rise will be, or how much sea level rise we will see over the next 100 years, between now and about the end of the century or the year 2100. On the far left-hand side, Meal et al. Is actually a part of one of the sea level rise projections, not a scenario necessarily, but a projection produced out of the Intergovernmental Panel on Climate Change based on a low emission scenario. And in the next three bars, there are a few Natural Research Council reports, one in 1987, one in 2011, and one in 2012. These were all done differently. The first two were sort of expert licitations or assessments, expert judgment on scientific literature. The other one included some new science and projections. And then the next four are what we call semi-empirical projections. So again, just trying to take observations from tide gauges around the U.S. and the relationship between the sea level rise we've measured at those tide gauges and global temperature, and integrating that into model projections. So trying to take some of what we've observed in the Earth system and building that into the model projections. And then finally, the one on the far right, Pfeffer et al., is a study that really tried to look at how much ice could we possibly melt, or what could be the plausible maximum contribution from ice sheets in Greenland and West Antarctica to sea level rise. So it's a big, wide range. It goes from about 8 inches to 2 meters or 6.5 feet. And that's a pretty wide range of possible futures. Next slide. So what we tried to do in the report is acknowledge that those futures exist, and showing the full range of possible futures, but then discuss a little bit about what needs to happen for these different scenarios to actually take place. So the lowest scenario is actually a linear projection of the existing trend. So in other words, if sea level rise continued at the same rate that it has over the past 100 years, that's what it would look like, and that's primarily a reflection of warming of the oceans. So as the global temperature gets hotter, the oceans absorb a lot of that heat, and as ocean water warms, it expands and sea level rises. That's one of the primary drivers of sea level rise. On the intermediate low scenario, half meter, shows you a scenario where ocean warming would occur more rapidly. And that's based on some of the model projections from the IPCC, or the Intergovernmental Panel on Climate Change. The intermediate high scenario, and as you move from the lowest scenario to the highest scenario, you're increasingly taking into account ice sheet loss. So ice sheet loss is a term that we use to refer to both ice sheets melting and discharging water into the ocean and increasing the volume of the oceans, and large chunks of ice sheets, land-based ice, where the ice sheets are above land, falling off and breaking off and falling into the ocean. So in either case, you're contributing, adding to the volume of the ocean and increasing the amount of sea level rise. So those are the two main drivers at this point. So as you move from this lowest scenario to the highest scenario, you're increasingly taking into account ice sheet loss. So the intermediate high is a projection, based on an average of climate model projections that take into account ice sheet loss, and the highest scenario is that based on that study that takes into account the maximum plausible contribution of ice sheets over the next century. It's really important to note that these scenarios are depiction for between now and the end of the century, but we don't expect sea level rise to stop in 2100. It will continue to rise as the ocean responds to temperature increase and ice sheet loss. Next slide. So in the report, what we did is provide a risk-based framing. And what we mean by that is provide, because we're not assigning likelihoods to any one of these individual scenarios, we tried to provide a confidence statement in the overall range. So we have very high confidence, a greater than 9 in 10 chance that global mean sea level will rise at least 8 inches and no more than 6.5 feet. And below the statement, I've included the sort of rubric, or the conditions that we used, or the qualifications we used to come up with that confidence statement. So the reason we have very high confidence in this large range is that there are multiple sources that point to this. There's consistent results, well-documented, accepted methods, etc. Now, you might say that it would help to know where we know to narrow the range somewhat. But if we were to assign a confidence statement to a smaller range, in other words, if we were to say that sea level is to rise between 1 and 2 feet, for just hypothetically speaking, between now and the end of the century, we would have to assign a low confidence to that statement, because there is evidence, and there are a substantial number of studies that point to higher amounts of sea level rise outside of that 1 to 2 foot range. So our goal was to be able to identify what we feel very confident in, but I would say that right now the likely, quote unquote, the more likely range is probably somewhere between the intermediate low and the intermediate high. We've provided the expanded range again under the auspice, or the idea that scenario planning, considering multiple scenarios in a scenario planning process, actually improves your sensitivity analysis and makes you better prepared for a range of futures. We've also done that because we understand that it's really important to consider low probability or low likelihood, high impact scenarios. Next slide. So again, we're talking about global sea level rise. We know, however, that sea level change varies regionally and locally. We have tide gauges across the U.S., for example, that NOAA maintains, and they show us differences in relative sea level rise. So there are local and regional factors that cause sea level to change and deviate from that overall global trend of rising sea levels. For example, in the Northeast, there are areas where the land surface is subsiding or sinking, either because of sediment compaction or groundwater withdrawal or tectonics. Another big example of that is in the Gulf of Mexico by New Orleans. The area around the Mississippi Delta is sinking rapidly, so the relative rate of sea level rise in New Orleans and other areas nearby, where you see those two red dots on the north end of the Gulf of Mexico, is actually quite higher than global rates. Conversely, in the Pacific Northwest and in southern Alaska, you can see areas where relative sea level is actually falling, which is, of course, different than the global trend of rising sea levels, and that's a result of the land surface rising or uplifting due to plate tectonics. So next. Nevertheless, when you look at all of these tide gauges, which all of those dots on the map have over 60 years of data, water level observations, and so we've just binned those tide gauge, those rates of relative sea level rise from those various tide gauges and color-coded them the same way as the legend on the map. You can see that a majority of them on U.S. coastlines are relatively similar to the global trend. Next slide. So one of the things that I was trying to highlight in describing the scenarios themselves, the scenario curves, is that, you know, I'm really active, an area of active research is what we know and what we don't know about ice sheets. And so we've really started to see over the past decade and have established now, including specifically in the National Research Council report from 2012, that at this point the biggest contributor to sea level rise and changes in the rate of global sea level rise, namely increases, is ice sheet loss from Greenland and West Antarctica. So we're seeing record rates of ice sheet melting and ice sheet loss, and we really need to get a handle on that. So it's an area of active research, but we're doing our best to understand, you know, how much that's going to contribute over the next 10, 20, 50 years, and even 100 years. Next slide. But one of the things that we're also doing is trying to understand how decision processes under uncertainty and human behavior actually factor into this, in taking this kind of information and using it in a coastal management context. So, you know, if ice sheet loss and the rate of ice sheet loss are a big uncertainty right now, I would say that actually how people use this information and how they make decisions is probably as big, if not a bigger, area of research. And so, what do I mean by that? How would you actually take and use this information and make decisions with it? Next slide. So, a lot of scientists like to come up with analogies, and in the case of sea level rise, a lot of times we have analogies for the process of the physical process of sea level rise. But in this case, what I want to do is draw out an analogy for how you might actually use this information, and take and use it in your management context. So let's say tomorrow there's a chance of rain and a 50% chance of rain. Maybe you leave a little bit earlier for work, maybe you use an umbrella, maybe you take a different route. But the consequences of you being 15 minutes late to work on most days really aren't that high. Now, let's say the same for the same day, you might have an outdoor wedding planned. And so the consequences of those conditions are a lot higher. You might have to rent a tent, you might have to cancel the event altogether, or you might have to find an alternative location. You may have hundreds of people depending on that choice, and therefore the consequences are a lot higher. Next slide. So this is how we've framed the scenarios based on higher and lower risk tolerance. So to draw that same analogy in the context of sea level rise, if you have an area, an open space area, or an area where you can accommodate you have a greater flexibility to accommodate flooding, the consequences of during a storm event evacuating that area and allowing it to be flooded are a lot lower. In other words, there's less critical infrastructure and not a lot of threat to lives. And you have the ability to manage that space differently in the near term. Then you have a higher risk tolerance, and you might consider something like the intermediate low or lower scenarios, at least for the near term, until you figure out a different long-term decision pathway. Conversely, if you have an airport that's right at sea level, like Oakland International, pictured here in the San Francisco Bay Area, you have very little flexibility to accommodate flooding because that would interrupt your operations. You have a higher consequence because there are ramifications for human health and safety and critical infrastructure and the disruption of the movement of goods through the Bay Area. And you have an inability to change in the near term. So in other words, it's not very easy just to pick up and move an airport. That you have a lower risk tolerance. And so you might consider what you would do, start considering sooner what you might do in those higher scenarios of sea level rise to get better prepared. So that's my presentation. At this point, I want to just run quickly through the tool. And so just to give you a better sense of how this information could be used in a real-life context, I want to show you how we took and used these scenarios to help people in the Sandy-affected region. In the wake of Sandy, you had a lot of people who were making rebuilding decisions, rebuilding homes, trying to restore beaches, and in the case of, say, New York City, really managing dense critical urban infrastructure. So NOAA teamed with FEMA and the Army Corps of Engineers and the U.S. Global Change Research Program to develop this sea level rise tool for Sandy recovery. And what we did, we were taking information from FEMA's National Flood Insurance Program on current risk and coupling that with sea level rise scenarios to give people an understanding of future risk. And that way they could actually rebuild for the future or a better plan for recovering coastal communities. The map has the tool has two components. It's a series of interactive maps, which I'll show in a second, and a flood elevation calculator that the Army Corps of Engineers that gives you some specific information on smaller timescale increments. And I should just mention that we actually won a Green Gov award from the President. The team that developed this tool won an award from the President under the category of Climate Champion for building this tool. So if you were to click on the maps and you would zoomed out, this is what you would find. We'll zoom in the area around Sandy Hook, New Jersey, just south of. And so what you can see here is in this yellow line, this is how FEMA, through its National Flood Insurance Program, defines the 100-year flood limit. And so what we've done is add the different sea level rise scenarios to the flood elevations within that 100-year flood limit to show you what, how those flood zones are going to change over time in the future. So again, if somebody is in this area, they may be considering how high to build or where to build, or even how to build. Maybe they want to restore dunes or more ecosystem function to be more resilient over time. And this kind of information, this tool puts that kind of information in their hands. And the last thing I'll say, just in closing, is that FEMA is actually endeavoring to build a similar tool in a few different pilot locations across the U.S. One of them is in Florida in the Tampa Bay region, another is in the Gulf of Mexico coastline, and finally we're looking at building one in the San Francisco Bay area. So a better segue to Ken, and Ken, I just want to introduce Ken. Ken has done a massive amount of work on the regional climate scenarios and is really to be commended for providing some really useful information with respect to what we know about the climate of various regions in the U.S.
Okay. Trust that I can be heard well, and we'll just jump right in here. What I will be showing here is some analysis we have done for the National Climate Assessment with respect to physical climate conditions. So these are things like, temperature, rainfall, and related kinds of atmospheric conditions that affect us as a society and affect the environment. I'd like to give you just a little bit of background here before I jump into some of the results. These are plausible projections of the future, as Anne said. These aren't predictions, but plausible outcomes based on certain assumptions about where we might go with respect to future emissions of greenhouse gases. There's a lot of work that goes on in the climate community with regard to trying to project climate. A lot of the work has centered around support for the Intergovernmental Panel on Climate Change, their assessment report activities. And as we started this effort, we really had two choices about the kinds of information we could use. There's been a whole set of climate model simulations produced for the fourth assessment report of the IPCC. This report came out in 2007, and this set of simulations of the future climate has the acronym CMIP-3. That stands for Coupled Model Intercomparison Project Phase 3, but let's just refer to it as CMIP-3. The fifth assessment report of the IPCC, the report on climate conditions, just came out, and that particular set of simulations, newer models, a little bit different in some ways, which I won't get into, and those are referred to as CMIP-5. So we could have used the older ones or the newer ones. The Federal Advisory Committee decided that the climate scenarios would be based on the older CMIP-3 model simulations. And this really was based on two factors. One was a timing issue. When we started this whole process of analyzing climate model simulations back around 2010, early 2011, the CMIP-5 models weren't all available. And so it would have been probably difficult to get them all done in time for all the chapter authors to work on their chapters. In addition, the CMIP-3 models have been studied extensively. They're well understood, and that was another reason for choosing those. So to produce our climate conditions, we used three different sources of information based on this. We used the data directly from these global models from the CMIP-3 archive. We also used data that have been scaled to higher spatial resolutions, and one set uses statistical methods to do that. This is a relatively cheap way of doing it. And another set uses more sophisticated ways, dynamical methods, where we actually run another model to produce the higher resolution data. So these are the three sources. So what I'm going to do now is just kind of jump in and show you some selected examples of the products that we have developed. So next. Okay, first of all, just to give you a little context here, This is just some general climatology, climate of the U.S., and it also shows the outlines of the regions that the National Climate Assessment has focused their description around. For temperature, as you can see here from the blue colors are cooler, reds are warmer. Of course, it's warmer in the south than the north. You also see that in the western U.S. that the higher elevations are cooler than the lower elevations, so very, very well understood pattern. If you go to the next slide, you look at the distribution of precipitation annually. Here we see a very pronounced east-west pattern where the eastern part of the U.S. is wetter than the western part of the U.S. The exception for the west being the coastal regions and the higher mountain regions. Wettest areas in the U.S. are extreme northwest part of the U.S., coast of Oregon and Washington, and along the central Gulf Coast. Driest areas are in the extreme southwest and kind of southwest Arizona, southeast California. Next. Okay, some of the things that affect the U.S. in terms of extreme conditions are just listed here. These have important impacts on the U.S. Droughts, floods, winter storms, various types of convective storms, tornadoes, hail, severe thunderstorms, heat waves, cold waves, and hurricanes. And in the National Climate Assessment, a lot of our discussion of conditions and what might happen in the future focused on these things, although I won't talk too much about these. Next. Okay, first of all, a little bit of context. What's been happening in the U.S.? So let me show you just a few graphics of our analysis. This shows the time change in annual precipitation, which is the top graph. This is averaged for the whole U.S. And we also show seasonal in the lower four panels. Let me draw your attention just to the top one, which is annual precipitation. If you look at the 20th century into the early 21st century, there has been an upward trend in precipitation. If you look at the year-to-year values, you see that there's a great deal of year-to-year variability. But overall, it's been a little bit wetter in the last 20, 30 years than it was in the early part of the century. And most of that increase actually has occurred in the fall if you look down at the lower four panels. Next, what about temperature? Well, temperature has been doing kind of the same thing. It's been going up. And if you look at this graphic of annual temperature for the U.S. going back to the beginning of the 20th century, you can kind of break it down into kind of three periods from the early part of the 20th century into roughly the 1930s. We had a fairly pronounced warming trend. After that, things kind of leveled off, and it even cooled somewhat into the 60s and 70s. And since that time, there's been rather rapid warming. I do not show the year 2012 on this. It only ends at 2011. 2012 is the warmest year in the record, and it's well above the previous record. It's about 3 degrees above normal. So it actually is at the top of this graph if I had included it. Next. Okay, here's another metric of what's been happening in the U.S. This is the freeze-free season. That is the average number of days between the last spring freeze, last occurrence of a freezing temperature, and the first fall occurrence of freezing temperature. And if you look at this, you also see a upward trend, and it kind of mirrors the temperature, the annual temperature, where you have an increase in the early part of the record into the 1930s, then kind of a leveling off or slight decline, and then a very rapid increase in the length of the frost-free season during the last 30 years. Next. And here's a graphic that shows the most extreme temperatures. It's essentially a heat wave index, and how that's varied over time. And these bars here show decadal values from the early part of the 20th century. I wanted to show this to just show you that when you do analysis of extreme heat, the 1930s, the Dust Bowl era, really stands out in the central part of the country. And actually, if you look at the U.S. average, which is in the upper right panel, you see that it also dominates that. So the extreme temperatures that we experienced in the summer of the 1930s are still kind of the heat of record in many parts of the country. Now, the last decade of the 2000s, we've actually seen in many of the areas, it's been kind of the second highest, the highest after the 1930s. And in the West, in the two Western regions, kind of the number of heat waves has been the highest during the last period, where the heat of the 30s wasn't quite as extreme. Next. Okay, now let's look at the model projections. And first, let's look at temperature. We looked at 15 different climate models, and the next graph shows how those, what the warming is in these models with respect to the latter part of the 20th century. A little bit of a complicated graphic here, but let me explain it very quickly. I have here, each of the symbols here represents one model, and it represents the temperature change for that model with respect to the latter part of the 20th century. I'm showing 3 periods here: early part of the 21st century, mid and latter part of the 20th century as you go from left to right. Different colored symbols represent 2 different scenarios. The red is a high emission scenario, which is more like the path we've been following, and the blue, which indicates B1, is a lower emission scenario, and I won't talk about the green. So if you just focus on the red and the blue, the red and blue circles give the model mean of all these models, and then you see the distribution about the mean. A couple things to point out here. Number one, all the models show warming for all of the periods. And the value of the warming is actually pretty significant with respect to the historical range of conditions. If you look at, and as you go forward in time, from early to latter part of the 21st century, the warming gets larger and larger. In the early part of this period, there isn't a lot of difference in the warming between the 2 different scenarios, but by the time you get to the latter part of the 21st century, there is quite a difference, almost a factor of 2 difference in warming. And if you look at the red, the high emission scenario, which again, as I say, is sort of the path or have been on, the warming values are really large. If you remember the previous graphic, kind of the largest value of terms of a annual value in terms of the how much different from normal it was, we were seeing the highest values of about 2 degrees. And the record for last year was about 3 degrees. If you look at these A2 values, what this is telling you is that the mean of a 30-year period for all of these models is considerably larger than the hottest year that we've experienced in our historical record. Okay, go on to the next graph. Okay, this just breaks it down by season, the same kind of presentation. We show winter, spring, summer, fall. What I wanted to show you here is that there isn't a lot of difference in seasons. In this particular set of models, the summers warm somewhat more than the winters, but the range of the models is larger than those differences. So the real message is that all the seasons are projected to get warmer under these scenarios. Next. What about the spatial pattern of warming? Well, this shows you a map now of how large the warming is around the U.S. And the basic message here is that there's not a lot of difference across the U.S. Hope that siren isn't bothering anybody. I can't turn that off. But anyway, there is some differences. There's a little bit less warming in the kind of coastal and southern regions of the U.S. and a little more warming in the interior of the country. But it's relatively small compared to the absolute magnitudes of warming. Next. Okay, what about seasons in terms of the pattern? This shows the top pattern. This is a different set of models now, which I won't get into. But the top panel shows the annual temperature. And then if you look at the bottom 4 panels showing the seasonal variations, just a couple of things to point out. One, if you look at the winter, what you see is quite a bit more warming in the central part of the country, in the northern part of the country. And this illustrates a pattern that we see most strongly in the wintertime, where the polar regions or more northerly latitudes tend to experience more warming than more southerly latitudes. And we're seeing this general global pattern expressed in the winter season here for the US. Second thing I'd like to point out is that there is more warming in the interior of the country in the summer, and fairly large warming. In these models, the largest warming actually occurs in the central part of the country in the summertime. And that's in part due to some drying out of the soils in the summertime, and that tends to increase temperatures. Next. Okay, just a couple of, or a few variables that we've calculated from the temperature values, just to give you a sense for some things that you might be able to connect the impacts more readily. This shows the number of days above 95, daytime high temperatures above 95. Top graph shows the change in that temperature, or the change in that number, and the bottom 2 graphs shows you what the current climatology is on the left and what the absolute values are in the future in the middle part of the century on the right. And I'll just draw your attention to the top graph and show you that in the southern part of the country, much of the southern part of the country would be projected to have 20 or more additional 95-degree days by the middle part of the century under the higher emission scenario. Next. What about on the cold side? Well, here we're talking about nighttime low temperatures that drop below 10 degrees. And the pattern here is now reversed in terms of a change. The larger changes in the northern part of the US, where in much of the north, the models project 15 or fewer days below 10 degrees. There's not much change in the south because in the current climate, you simply don't get many of those, if any, in the far south. Next. This shows changes in the frost-free season length. If you remember the graphic I showed before, I didn't point out what the changes were, but over the 20th century, there's been about roughly a 2-week increase in the length of the frost-free season. This shows the changes for the future under a lower emission scenario, bottom graph, and higher emissions in the top graph. And I'll just draw your attention to the top graph. By the middle part of the century, these models would project increases over much of the country of about a month. So about double what we've already experienced during the 20th century. Next. A couple more graphics here related to temperature. This shows number of cooling degree days. This is a metric we calculate from temperature that we can relate to the amount of energy that's used for air conditioning for cooling purposes. And so here we might expect with warmer temperatures we get more of these, which would indicate more energy being needed for cooling, and indeed we see that in this graphic. And the largest increases are once again in the south with changes of 800 or more cooling degree days. This represents increases of 20–25% or more. So it's actually quite large increases in the amount of energy that might be needed for cooling. Next graph. This shows the flip side, a metric we call heating degree days, which is related to the amount of energy you use for heating in the wintertime or in the cold season. Here the largest changes are in the north, where you now have the largest heating bills for warming up buildings. The changes in the north are around 1,000 of these units or more. That's about a 15 to 20% decrease in the amount of energy that might be required. Okay, next. Let me go very quickly to a couple precip changes as we're getting kind of late here, and I'll try to hurry it up here. I want to point out just a couple things with precip. One, this is the same kind of graphic where we're showing each of the individual model projections of precipitation change for the U.S. And what I want to draw your attention to is where the zero line is in this graphic and where these points are scattered about. And what it says on a U.S. national basis, the models are kind of both projecting increases and decreases, and the range of model projections, or the uncertainty of model projections, is actually a bigger part of the story than the model mean changes. So we don't know nearly as much about precip, or can't say as much about precip. Next graphic, and actually, oh, let's go on. That's the seasonal values. Let's go on to that one. Yes, right there. This is very important. I want to spend just a minute on that, and then I'll just stop. This shows the pattern of precipitation changes over the U.S. for the 3 different periods: high emissions on the left, low emissions on the right. Now draw your attention to the bottom left panel. You notice here the brown colors in the southwest, teal colors in the north. What we're seeing in the models is a very robust projection of drier conditions in the subtropical latitudes and increases in precipitation in more northerly latitudes. And what we're seeing here for the U.S. is indication of that global pattern. And so what it means for us for precip is that kind of the rich are projected to get richer, and the poor get poorer. Dry areas of the U.S. are projected to get drier, and the wetter areas of the north are projected to get wetter. And I'll stop right there.
Great, thanks, Ken. Okay, thanks, Ken. And thanks everybody for your questions as well. And that was an amazing amount of information in a very short period of time. And so hopefully what you're able to do is to go to some of the resources behind this as well to learn more. And we'll put a slide up with those bits of information while we're talking about questions. And certainly when we send out the email after the webinar, we'll send out where you can find all of this information, because it's a lot of information to take in all at the same time. So I'm also going to put on my webcam so you can see us answering questions, not in the dark though. So there we go. And there's Ken as well. So we got Adam and Ken and me. So we're going to go through a few questions that have come in, and thanks very much for some great questions. So first of all, I know, Adam, your time is limited for the rest of the afternoon. So I wanted to get a few questions in on the sea level rise stuff first of all. So one question was, in the sea level rise scenarios, does it only take into account melting from Arctic ice in terms of sea level, or are there changes in ocean circulation that are involved there too? Particularly if we have a lot of Arctic ice melt, or particularly from Greenland, does it change the North Atlantic circulation, and are those in your scenarios?
That's a great question. Actually, what the real driver behind the differences in the rates and magnitude of sea level rise in our scenarios is actually land-based ice, changes in land-based ice. So in other words, contributions to the volume of the oceans. Now, as there are changes in ice sheets, and that contribute to the oceans, that does have an effect on ocean circulation, as would changes in sea ice. So we don't really reflect that as much in our scenarios, but I think that in the regional chapters of the National Assessment, and even in the regional technical input reports that are already available online, there's a lot of information on some of those more regional and perhaps even in some cases local effects where circulation changes are happening. For example, we know that some of what was happening in the Northeast in that map on the tide gauges that showed slightly higher rates of sea level rise may be due to ocean circulation as opposed to changes in vertical land movement, which is what I was explaining when I had that map up.
That's great. And another question sort of following on from that. And by the way, I should point out that you should be seeing a slide right now with some of the URLs for where you can find information. The very last one there is globalchange.gov, and that's where a lot of the information, the early draft of the National Climate Assessment can be found as well. So a lot of this additional information you just mentioned, Adam, you can find there. And it's got the URLs for how you can get to the scenarios, which also include downloadable images and graphics and lots of information about behind each one, as well as the reports that both Ken and Adam led on these scenarios. So another question about the sea level, Adam. So you mentioned that the Hurricane Sandy tool should be more available through FEMA for other areas as well. Do you have a sense of when that might be for people, and or whether there's more granular information that people, what do people do with sort of the larger scale information that you presented? Can they translate it for their particular location?
Yes, absolutely. So I'll take those questions in reverse order. So actually NOAA has resources. NOAA and the U.S. Army Corps of Engineers both have resources. NOAA produced a report which we can provide the link to on how to use sea level scenarios, and it sort of walks you through step by step how you would take the global scale information, try to integrate as best as possible local and regional factors like vertical land movement and ocean circulation, and then arrive at scenarios of sea level rise that are relevant for your neck of the woods, so to speak. Now, with respect to using that information in a planning process, I would say that it would be really important, because there are a range of different actions that you can take or management measures that you can take. I think the most important thing is to get connected to experts who understand the problem and who can help not only get you to the relevant pieces of information, but also help facilitate discussions about how to identify options for management actions that you can take. And so NOAA has the Coastal Services Center that has offices across the U.S., and then we have Sea Grant colleges, which also provide a network of experts that you can connect to. So I would say it's really important, particularly as the science evolves, to get connected to those experts. And I'm sorry, the first question was?
The first question was whether the FEMA expansion of the Hurricane Sandy tool, when that would be available.
Yes, well, as you know, the wheels of government turn so quickly. But it's, I would say the first pilot, which I think the first pilot started in San Francisco, so that one is, I think, moving along and probably might have some products to look at in the summer of 2014 or maybe the end of 2014. So a really critical component of this is going to be the engagement process to sort of walk people through what's in the tools. So it's not going to happen overnight, but I would say that since the President's Climate Action Plan and since there was a release, FEMA released a report on climate change and the National Flood Insurance Program, these kinds of initiatives are moving more quickly.
Great, and we'll try to capture all of that as well when we send out the email with some additional resources, because it is happening very fast, relatively speaking, for the federal government. So a quick question for, well, either of you, but perhaps Ken. One of the question was, what's the difference between prediction and projection? And following up for that, how do we use them differently?
Well, probably the big difference would be that when we talk about a prediction, we are generally talking about something that happens in the physical climate system that we understand the basic physics of, and we think we can, with that understanding, predict what could happen in the future. With these scenarios of climate that we're talking about, these projections, they're dependent upon not only what's happening in the climate system, but what decisions society will make, or what path society will make in terms of emitting greenhouse gases. And so it's a much different kind of problem. So how to use them? Well, that's a $1 million question. Maybe, Anne, you should take over there and address that.
Well, actually, in response to the poll question that was asked at the beginning, or near the beginning of the webinar, lots of people were saying that rather than reports, it's much more useful to have interactive sessions in terms of how to incorporate scenarios into the decision process. Workshops, for example, were the most popular way of potentially using these. And so I think we're going to take that information back in Second Nature for sure. And the output of our expert panel, which we hope will be in the spring of next year, that to me seems like that we will consider partnerships and getting this out in a much more interactive way for people to actually incorporate. In the meantime, I think having these scenarios and this sort of what-if planning, plausible future kind of approach, you can start to have sessions even on campus about what this might mean to the valuable elements of your operations and your community. So for example, if it's important that students are able to commute to campus regularly on a daily basis, for example, if you're a community college, in particular, where a lot of your students are living in the community at large, then you obviously want to make sure that those transportation routes and the accessibility to campus is of paramount importance. And so you can start to look at what are the real drivers in terms of your values on campus and in your operations that climate might impact. And I think we will follow up at Second Nature in the next several weeks about what we can do to help facilitate those processes. Sarah, I don't know, Sarah Brylinski is also on the phone from our Boston office at Second Nature. She's the manager or the director for the resilience program here at Second Nature. I don't know if you want to say anything else, Sarah, from that perspective.
Just taking a second to unmute myself. I think you covered it, Anne. You know, applying any of this work to higher education, much like applying any of this to any industry, is such a diverse and varied perspective. We could break down sort of the application or you know, the potential use to higher education depending on where we were talking about or the types of institutions we were focusing on in a number of different ways. But you know, in future, you've talked about this already, but in future iterations of this series and in other resources that we offer, we hope to get more in depth with that. But to the extent that folks in the audience and people who are on this call or who are interested in this topic can provide us with feedback about, you know, specific questions or, you know, what would be useful in this regard, that would be tremendously helpful to us as we dig deeper into some of this.
So do we have time for just one or two more questions? One question that was asked is, can we get information at a higher granularity, higher resolution for use in regions smaller than what we've talked about in the National Climate Assessment? And that could be to either of you, I think, but perhaps Ken.
Yeah, we want to make these data available. Right now, we're still under the review process in the National Climate Assessment, and so we can't provide kind of the underlying data yet, but our intent is to do so once the report is published. And some of the underlying data is at a fairly high resolution, maybe you know, as fine as 10 or 15 miles, kind of spatial resolution. But whether or not you want to really get down to that level or not, I think you have to do carefully. But I think getting the data at a resolution that's higher than these 6 regions, or 8 regions rather, that we've organized the assessment around is we expect to be able to do that. Depends on what data you're talking about. Now, if you're how detailed the data is that you need for your application.
Adam, you have any other thoughts on sea level rise particularly, but other things too?
Sure. Yeah, I would say that the report that I referenced on using scenarios, it's actually using local scenarios for sea level change that NOAA produced is a good one. We have data that is maintained that actually helps provide some finer resolution than the global trends. But I definitely think that in all cases, as you move from sort of some of these global trends and further information about environmental change further out in time to shorter time horizons and finer spatial scales, you have to wrestle with how you're compounding uncertainty when you try to integrate different types of information and different analyses. And so that doesn't mean that information doesn't exist that can help you make decisions for your planning area, but it's really important to consider, the different sort of assumptions that those studies were made under and the different uncertainties with the underlying data sets for that analysis.
Yeah, I'll just add to that as well. I mean, what we found a lot, I think, in terms of how communities are making decisions that really make sense for their systems is higher resolution information is useful, but it isn't. Turns out that it's probably not the defining factor in what a more useful process. And so, actually gathering people in the community or people on the campus together to look at the system as a whole, and this sort of participatory scenario planning process turns out to be very helpful in defining the problems and the vulnerabilities, and then how you factor in some future climate changes. The uncertainty in the future is by far the biggest factor in how we would sort of need to consider those changes. In other words, we could get higher and higher resolution, but because of what Adam said, your uncertainty grows even greater at that point. It's probably not the most useful. What we do see with the climate in particular, I think there's a number of impacts already happening across many of the regions. Certainly we've seen some impacts from storms in recent months, even just this week in the Midwest. We're seeing really consistent changes in heavy precipitation across all regions of the United States. And so that's one of those factors that you can sort of, we're already seeing it, we expect it to continue. You can sort of count on as being a problem for most campuses and most communities. This spring on the East Coast, for example, there were lots of issues with heavy precipitation for fairly prolonged periods of time. So then these are causing millions of dollars of damage at this point. Certainly we know heat is going to be an issue, and whether you're running football practice or you're trying to manage the heating and cooling costs on campus, those are certainly factors to consider. And these scenarios that we talked about today, the cooling degree days, for example, or the heating degree days, those are very useful in trying to project your changes in heating and cooling needs. So I think there's a lot of good information here, but incorporating them into this sort of participatory process really seems to be very effective from what we've seen. And what we'd like to do is to explore that further through facilitated sessions in Second Nature.
Yeah, and if I may, to follow on that, I mean, I think that's a really great point. Once you have the information or you settle on the information that you have, there's still the process of actually making the decisions, as you pointed out in your presentation. You can pursue those in parallel. In fact, an example, just to give folks for this call, the University of Michigan has been doing an adaptation assessment with the city of Ann Arbor. And one thing that they're doing is saying, if the climate in the future in Ann Arbor is going to look more like what the current climate looks like somewhere in a more mid-latitude, mid-Atlantic kind of city or state, then we can actually look at what those cities and states do to manage those kinds of conditions, and we could start to think about what that would mean in terms of managing the operations on our campus and in our city. So actually doing some sort of participatory assessment and some research on what actions you could take that line up with the kind of climate conditions and other conditions that you might expect in the future.
That's great, and I think we are more than happy to, in fact, we really solicit feedback on what would be helpful to share in terms of, is it case studies about how other campuses have dealt with adaptation, or, is it sort of decision-making guidance, and so we started to get at that today. We hope certainly to hear more from everybody. I think we're about out of time, and we have a few questions. We'll definitely send out an email after the webinar with where you can find more information. And we thank you very much for joining the webinar. This was a great session. We're so glad that Ken and Adam, you could join us. And hopefully we will hear more from people as the weeks and months go on as well. So thanks to everybody.
Thank you.